Hello everybody, welcome back to another Gregorious Matter You. In this video we're going to be looking at cofibrations, okay? And as much as I want to get into this topic because it's one of my favourites, okay, and I find it really fun and satisfying chasing diagrams, first I want to give a shout out to CXMP, okay? If you're looking for a refresher or some prerequisites to this videos, or anything like that, go to CXMP. He's doing an A-level maths channel. He's going to be doing maybe some early university stuff later on in his channel, okay? Even if you do know the A-level stuff, which you probably should for algebraic topology, and even if you do know the early university stuff, which you probably should for the algebraic topology that I'm doing right now, do just subscribe. You don't have to turn notifications on. Leave a like, nice comment, something like that, just, yeah, because, you know, he's much more organised, and in these times especially, lots of A-level students will be needing him, so yeah, do just, you know, leave a like or something like that on his videos, you know. Anyhow, link will be in the description, okay. Anyhow, cofibrations. I'm really bursting to get into this topic, okay. So first we have to define the homotopy extension property, or just define a cofibration. So a map I, which takes you from A to X, is a cofibration, okay, if it satisfies the homotopy extension property. Meaning that if H compose I0 equals F compose I in the following diagram, well, of course, A goes via I to X. Right, now X goes via I0, which I'll explain in a second, to X cross I. And now A goes via I0 to A cross I. Now via I cross the identity, we have A cross I going via I cross the identity to X cross I. And we have a space in the middle Y, which I'll talk about in a second, but for now it's just some generic space Y. Right, now we have a map F, which takes you from X to Y. And we have a map H, which takes you from there to there. Now C, F compose I equals H compose I0. Alright, there must exist a H tilde. Does not have to be unique, normally isn't, but there must exist a H tilde to make this diagram commute. Alright, and the H tilde is this, okay? Goes from X cross I to Y. This diacom, okay, and I0 of X is equal to X0, okay? Now the first thing we're going to prove is that push-outs of cofibrations are cofibrations. If you don't know what a push-out is, I know for sure that there's a Wikipedia article and on push-outs, and you definitely should know what colimits are to understand them, and if you don't, then I've got the definition of a colimit in the last video, okay? But okay, here goes. We normally write, well, in this video we're going to write at least, but I think this is normal notation, B like with a little union sign and a subscript G here, X, for the push out of a given cofibration, I, which takes from A to X, and a map G, which takes from A to B. Okay? Now, the theorem we're going to prove is the following. If we're given a cofibration I, which takes from A to X, okay, cofibration, alright, and any map, let's say G, which takes from A to B, then the induced map which takes you from B into, well, this, push out here, not sure how to say it, to be honest, I'll just, write it, okay, is also a cofibration. Okay, and for the proof, it is vital to notice the following. So, proof. Notice that B, and then you push it out with this map G, and then you do that cross I. This is isomorphic to B cross I, and then you push it out via G cross the identity, okay, to X cross I. Okay, these two are isomorphic. Now we're ready to do the proof. And this is going to be a diagram chase, and this makes me feel like James Bond, so I'm really excited to do this. So first, we use this diagram here, but we're going to enlarge it to, do the central a little bit more. Alright, so we have A, we still have A, and this still takes you via I to X. Okay, we still takes you via I to X, okay. We still have X going via I0 to X cross I. We still have A cross I going via I cross the identity to X cross I. And we still have this. Okay? But now, here comes the difference. In the middle here, we have our push-outs going on and stuff like this. Now, let's take a look at a bit easier, because we know that G goes from A to B. So let's just do that. G goes to B. Now we still have the space Y. Okay, in the middle. Don't forget that. Okay, now, to get this push out, okay, this side is a bit easier because we have B taking you via some map, induced map, to B, basically this, I don't know how to say it, as I was saying again. Okay, this push out here. Alright, and we have X taking you via some map here. Now notice that from the definition of push out, A is the common domain, okay? This is like this is the object, okay? Right, and now from the definition of a cofibration, we must still have a map F, which takes you to Y, okay? Now, this here goes via some map, okay, to B, alright, and then we cross I. Okay, now, we're going to use this fact here. We have A cross I going via G cross the identity to B cross I. Alright, now, sorry, let me just make this a bit of a larger arrow. To B cross I. Now, B will go to B cross I, this map, okay? And now, we can map B cross I onto this, okay? And we still have to have this H here. H. Alright, now this is where things get fun, okay? Alright, so we just have some map taking you from here to here. But here's where things get fun, because we have a H bar, which goes from X cross I to Y. Alright, from the definition of a cofibration, remember that this outside diagram, on the outside, is still a cofibration. So we still have to have this X cross I going via some, it doesn't have to be unique, but via some map. In this case, we're going to call it H bar, okay, to Y. Sorry, hay fever's killing my eyes. Right? Now, Now, from the definition of a push out, okay, we're just going to write that this is a push out, okay? From the definition of a push out, we can induce a map H tilde which takes it from here to Y. And why is this? Well, if you look at the last video where I introduced the definition of a colimit, okay, this H bar and this H, they're acting kind of like the epsilons, okay, and this space Y is acting like A. I think that's how I denoted it, okay. Alright, now, for this to be the colimit of this right-hand side diagram, like this half, there must exist a H tilde to make this diagram commute. Oh, look at that. We have B here acting as X. Boom, it maps to X cross I. We have A, like B acting as A, going here. We have this, bam. We have this, bam. We have this, bam. Okay? And now we finally have our H. We have our F. We have our H tilde. We have our H tilde. Boom. Booyah, bada boom, bada bam. It's QED time. That was really cringy. I don't know why I did that. But yeah, we're going to look at mapping cylinders now and the criterion for a cofibration. Alright, so we looked at cofibrations with a general space Y in the middle of the cofibration, well, in the middle of the diagram, kind of the cofibration. But actually, there's kind of a universal space which is normally used for cofibrations, namely the mapping cylinder. And this MI, alright, so I is some map, okay, and it's defined as the following. So it takes the codomain of I, in this case X, and then it pushes it out via I to the domain of the map cross I, the interval, okay? And this is how it's defined. And the reason we're going to do this is because now we can use this construction here to decompose arbitrary maps, let's say F, from some X to some Y, right? So if we have F, which takes you from X to Y, okay? Sorry, takes you from X to Y. Now recall that MF equals, well, we have the codomain Y, and then we push it out with F, okay? Okay, to X cross I, okay? And now realize that F coincides with the composite, and I'm going to explain the definitions of these maps shortly. So we have X, and that maps via J, which is some map which I'm going to explain in a little bit, to MF, and then that maps via R to Y, alright? And J of X is simply defined as X1, and R, well, R of Y is equal to Y on Y, okay? But on X cross the interval, R of X S is just equal to F of X on X cross I, okay? Alright, so this is how we define R, this is how we define J. So F coincides with this composite, this arbitrary map F coincides with this composite here, right? And now notice that if we have I being the inclusion mapping, which takes you from Y to MF, then notice that R compose I equals the identity, okay, because remember, R of Y equals Y and Y, but then we will have the identity when we compose it with I, okay, and I compose R is homotopic to the identity. Okay? Now we can construct some retraction H, which takes you from MF cross I to MF, okay, such that H of Y T is equal to Y, and H of X S T equals X, and then we do 1 minus T multiplied by S. That this map H goes onto I of Y. Now remember, I is the inclusion. This map H goes onto I of Y. Remember, goes from Y to MF. This goes from MF plus I to MF. Okay? And also, we can see that J, okay, and J takes you from X to MF from our original composite. Now this J, we can see, you can check yourself, satisfies the homotopy extension property. Satisfies HEP, I guess you can say. Alright, so this J satisfies the homotopy extension property. And now you can check this directly quite easily, but now we're going to come up with a criteria for a cofibration. We have to first define an NDR pair. Okay, so an NDR pair is a space X and a subspace A. Okay, so we have a space X and a subspace A. Alright, and this is an NDR pair, which means neighborhood deformation retract pair, but I'm definitely not going to write that all out. Okay, if there is a map U which takes you from X to the interval, okay, such that U, the pre-image of 0 under U is equal to A, and there is a homotopy, there is a H which takes you from X cross I into X, okay, such that H0 is equal to the identity, okay, H of A T is equal to A for A in A and T in the interval, and H of X1 is in A for U of X less than 1. Okay, now if U of X is less than 1, if U of X is less than 1 for all X in X, then XA is a DR pair. Okay? Now, cofibrations will just behave homologically like these pairs, okay? And we're going to prove a quick lemma about these pairs. Well, the lemma kind of proves itself, okay? You can check for yourself that it holds, but it kind of proves itself. Okay, there'll be XA and YB, for example, but we're just gonna, represent them with the maps. So if we have a pair let's say HU, that will represent XA, okay? And let's say we have, I don't know, J, for example, and V, okay, represent those things as NDR pairs, okay, then KW represents the product pair, okay, and what it represents is the pair X cross
I,
and then we have X cross B union A cross Y, okay, where W of X, Y is equal to the minimum of W of X, Y is equal to the minimum of U of X or V of Y, okay, and I'm just going to cut out the part where I write how to define K because it takes ages, okay. I wrote out the rest of the theorem, and sorry, the product pair is X cross Y, not X cross B, sorry for the confusion, okay. And you define K of X, Y, T in this way. I'm not going to read it all out because it's really long. It's a piecewise function, okay? And the theorem states that if either of these pairs are DR pairs, then so is the product pair. And the proof is really easy. What you do is you set V of Y equal to 0. And now if V of Y is greater than or equal to U of X, then that means that U of X must be equal to 0. That if Y is in B and X is in A, then we must see that K of X, Y, T is equal to X, Y, and it's really easy to check this continuous and well-defined homotopy that we want. Okay? And yeah, we're just going to look at cofiber homotopy equivalence, and then we're going to finish the video. Cofiber homotopy equivalence. We have to define a space under A, and a space under A is just a map I, which takes you from A to X, okay? And a map of spaces under A is a commutative diagram. Alright, so we have A, and it takes you via I to X. That takes you via F to Y, and A also takes you to Y via some J.
homotopy of maps under A
is a map H, okay, such that at each point, at each time T in the interval, H is a map under A, and if this H is a map under A, and in this case we write H as a homotopy between F and F prime rel A, and H of I of A, comma T, is equal to J of A. And yeah, this notion is called cofiber homotopy equivalence. In the next video, we're going to be looking at fibrations. See you then.